area of anaerobic digestion in our industry that all of us have experienced to one degree or another. And so I'm really, really pleased to be able to have the three presenters here today. My name is Brian Sievers. I'll serve as your moderator. If you were able to participate in the 11:30 session when it was the farmer panel, why you heard plenty or enough about me, so I won't say anything more other than I am a farmer and a producer and also a director of government relations for Raceland Alternative Energy, and also serve as director for the Horizon 2 Climate Smart Commodities Grant Program. Also the husband to Lisa, who's sitting right here. She's my business partner for 43 years and married to her for the same amount of time. I'm never going to make that mistake again that about a year and a half ago, I was giving a tour to some folks from Iowa State University at our farm and our anaerobic digester facility, and I mentioned that I'd been married to Lisa for 32 years. Well, I was 10 years off. And so, I learned my lesson the hard way, generally. So, but thank you for participating and coming not only to the conference, record-setting conference. We're nearing 1,800 people registered for the event. So we're really, really excited about the size, the scope, and also the opportunity to talk to you about some new and emerging ideas and concepts and approaches to anaerobic digestion. And I'm going to introduce each speaker as they come to the panel or to come to the podium. And so I will start with Dr. Tom Richard. And Dr. Tom is a professor emeritus of agricultural and biological engineering at Penn State University. For over 3 decades, he's applied fundamental engineering science to microbial and agricultural systems, developing market-based strategies for more sustainable agriculture and emerging bio-based economies. So we're very welcome to have you here today. Tom?
Thank you, sir. Thank you, Brian, and thanks to the ABC for inviting me and for hosting this panel. So I'm going to share with you kind of an overview of why Grass2Gas is so important. And I'll just jump right into my slides. And I'm going to come back to this cover slide a little bit because this is one of the grasses we'll talk about today. Cereal rye or winter rye, it's oftentimes grown as a cover crop, and that's one of the really important targets. But I want to start out by basically sharing with you a tale of 2 grids. So when we talk about renewable energy and the grid, most people are thinking about the electric grid. And most policy has focused on the electric grid, and most progress has happened on the electric grid. Right now, the electric grid is about 40% non-fossil energy. Half of that's nuclear, the other half is renewables. About half of the renewables are hydro, but there's been rapid growth of solar and wind over the last decade and a half, and it's continuing to grow. The natural gas grid actually would have been really boring if I put the supplies on, so I put the uses on instead, because the actual renewable natural gas fraction is less than 0.4%. So 100 times smaller fraction of the total grid in the gas grid than for the electric grid. And that's because we haven't been paying attention as a society to that grid. Other than for transportation, we haven't been building a policy infrastructure to support renewables in the gas grid. And the transportation component of the gas grid is so small that it actually didn't even show up on the graph. I had to fake it with a solid line at the bottom that you can hardly see. If we look at the opportunities for making renewable natural gas through anaerobic digestion, most of the focus has been on landfills, agricultural waste, particularly livestock manures, and wastewater treatment plants, and increasingly food waste. So you can see all of those on this graph, and they're the small bars. And if we got all of those, we would be perhaps getting about 4 or 5% of the natural gas grid into renewable natural gas. If we add grass to that portfolio, then we start getting into the big lines. Winter cover crops and prairie biomass are two that I want to focus on, and we'll be focusing on today. But also crop residues, and most of the crop residues are from grasses as well, corn being the most obvious one, but also straws from various grain crops. And those are big opportunities. Actually, the prairie line here would have gone off the chart, but I didn't have room. It's potentially quite a bit bigger. You'll be hearing a little bit from Will Higgins about the Horizon 2 project that Raceline's working on, and I just happened to put their targets, the impact that they'd like their particular approach to have here with the diamonds. If we got everything on this chart into the gas grid as renewable natural gas, then we would actually get up to 17% of the grid capacity today. Not 40%, certainly not 100%, but a much bigger percentage. And in fact, in the transportation sector, this industry, your industry, has had incredible success. So here's the growth of renewable natural gas as measured by the RINs credits traded through the EPA system. And they have grown dramatically. The red line is the Energy Information Agency's estimates of natural gas demand for transportation. And you can see it's growing too most years, but not all the time, not steadily. And at least from the preliminary Energy Information Agency data, which was just released last month and is likely to be updated in September, there was a drop last year, and it may be that renewable natural gas actually exceeded the need for transportation fuel. So as long as our policy structure to support the renewable natural gas sector is solely about transportation, we have a problem. We're about to saturate that if we haven't already. And that's not a good thing for our society, because there's a lot more potential. So if I took those bar graphs from a couple of slides ago and I put them on this same chart, which I've now shrunk down so you can barely see it at the bottom of the slide. Those blue bars are the same ones on the previous slide. The red line is the same one on the previous slide. And the green line at the top is what that potential is for renewable natural gas if we get the grasses and the manures and the food waste and all those other organic opportunities into the marketplace. And by the way, this scale on the left is not linear. So again, I just ran out of room, but it's actually 5 times roughly the scale there. It goes from 1,000 up to 5,600 at the top with a big jump, right? So what we need to make that jump are new markets and new policy incentives. And we've heard quite a bit today, both at the keynote panel and the earlier sessions, including the policy session, about what some of those new markets are, and a little bit about the current policy incentives. But one of the things I want to reinforce is that those policy incentives for those new markets for renewable natural gas are not sufficient. And when I talk about them, I'll talk about them more very briefly. I want to focus on a couple of sectors. The first are the areas which are really hard to decarbonize. And I apologize to those of you in the back who probably can't see the small letters here, and maybe not even the big ones. But the sectors on these two charts, these two pie charts, are transportation in blue, industrial in orange, commercial in tan, kind of at the bottom, and residential in light green. And each of those is broken up into lots of little components. And this is a projection based on a very aggressive electrification of the grid and an attempt to decarbonize these industries, primarily with electric substitution or substitution of renewable electric for fossil electric. And what you see are some pretty substantial gaps where the dark blue or orange or tan or green on the right are the areas that can be electrified. And the lighter shades are the areas that are really hard to electrify and therefore really hard to decarbonize. And so if you're sitting up front, you'll see at the left side aviation in the transportation. At the upper right, you'll see shipping and marine. You'll see heavy-duty vehicles up in the very left at about 11 o'clock or so. In the industrial sector, the really big area is in the chemical industry, and there it's used both for thermal energy and also in many cases as a feedstock, but also the steel industry, the concrete industry, the pulp and paper industry, and the construction industry. So these are all sectors of the economy which are very important to our society and which are not going to electrify quick enough, and for which thermal energy, such as renewable natural gas, can combine is absolutely essential. And there are some other things as well. There's a lot of talk about in the electric grid the challenges of matching supply with demand, especially as we have increasing intermittent sources of renewable energy like solar and wind. Energy storage is really expensive. Renewable natural gas can be stored in the gas grid, where there's about a month of storage already bought and paid for that's really cheap. And by the way, the electric grid is stabilized and peak power is provided by gas turbines that will run without any infrastructure changes or investment on renewable natural gas. So in my mind, there's no reason that renewable natural gas isn't competing against batteries instead of competing against solar and wind in the electric grid. And batteries are far more expensive per megawatt hour than solar and wind. But we need a different kind of incentives. We need incentives for both the capital cost of digesters and the operating cost of digesters. We need incentives to drive the industry and the profitability of this sector into these new markets so that we can achieve the potential for the gas grid that is already well underway for the electric grid. So grass is a huge part of that. It's at least 70 or 80% of that potential. And right now we do very little of that in the US. Example that I'll spend a little bit of time on are winter cover crops because they're low-hanging fruit. We have over 100 million acres of land in the United States, which is fallow in the winter, and where we actually know for conservation and water quality purposes, we should be planting cover crops. And many farmers do, but more farmers don't, largely because there's no market. Oftentimes the subsidies that are available for conservation plantings don't even cover their costs. And about half of US farmland is rented, and there's no incentive to the landowner to invest in something that doesn't pay, and certainly no incentive to the land manager, the farmer, to lose money with these kinds of programs. So generating new markets is really important. Cover crops, as you may well be aware, are planted in the shoulder seasons of the summer, in the fall. They germinate and green up the soil again in the fall, hold that soil and reduce erosion and suck up nutrients through the winter and spring, and grow really rapidly before the summer crops are planted. They're cool season plants, so they have a different kind of photosynthesis. They can take advantage of all that sunlight that's coming down on the soil. And by the way, here we are almost to the summer solstice, past the summer equinox, well past the spring solstice. And our warm season summer crops still really aren't happy. They don't really germinate well and don't really grow quickly until it gets hot. So this is a window in the farming season which those summer crops are really not nearly as productive as the winter crops can be. And they can be sucking up nutrients, improving water quality, improving soil quality, and providing renewable energy to America if we can figure out how to handle them. So this is just an illustration of how that can be done by Andy Higginsteller. Andy actually did his undergraduate at Penn State, where I taught for the last 20 years, and then did his graduate work at Iowa State, where I also taught for the prior 8 years. And so he was a great contributor and interdisciplinary thinker. So we did some analysis of what the yields would look like for winter rye as a cover crop, looking just at land that was in fallow, that wasn't being used in the wintertime for productive purposes. And of course, there are some advantages to being a little bit further south in those temperate regions of the Corn Belt. This is, across Iowa, Missouri, southern Iowa, Missouri, Illinois, Ohio, and into Pennsylvania, which I like to remind people is the eastern edge of this Corn Belt in the United States. And we can get 6 or more metric tons per hectare off of our farmland and that's dry matter from this crop. As you can see in the right side, if you look at the county level quantities and add those up, it's about 150 million tons a year of dry matter without any competition with food crops, with soil and water quality and diversity benefits that we are poised to take advantage of. This is a shot of my home garden last week. Cereal rye that I planted in the fall, a little bit late, honestly, but it's right now at about the ideal stage for harvesting for biomass. It's called boot stage, and that's because if you ever had jeans that were designed to fit over a cowboy boot, there's a little swelling down at the bottom, and you can see that swelling here. Let's see. This is a stalk of rye, and you can kind of see the seed head coming up here out of the top, and down below you see the swelling there, and here's another one that's swelling. So I want to emphasize, this is a cellulosic plant. It is not yet a food crop. It's got some emergent starch, but it's got a lot of protein in it, and the lignocellulose is there, but it hasn't gotten as recalcitrant or difficult to break down as it would if we waited until it was straw. So it's actually an ideal material to feed digesters, which actually ruminant farmers already know because in my neighborhood, they harvest it for silage. But many farmers who could be growing this don't have ruminants to feed it to. So this is an opportunity for them. I want to also emphasize that growing these cover crops for harvest can actually improve their water quality benefits. And this is something that the conservation community and some of the environmental organizations don't yet fully understand. That is true even if we fertilize these crops, which is a real eye-opener, but based on some very simple science. So it turns out if you fertilize these crops, they will grow faster, they will send down their roots deeper, and they will suck more nitrogen out of the soil from areas where their roots couldn't reach otherwise, so they can reduce the amount of nitrogen that can leak into the groundwater or into streams. And if we harvest those crops, we then take all that nitrogen off the field, which is better for water quality than if we kill it chemically and leave it on the field, where all that protein will dissolve and degrade into nitrogen that can then run off into the streams. So it's actually an improvement over the traditional cover cropping strategy. And this is the work that I did with the USDA Agricultural Research Service on field plots in Iowa, but it demonstrates that, and it also demonstrates that at modest levels of fertilizer at 60 or 90 pounds per acre, we can actually get really good yields from this material. We've also done some work on the carbon benefits of this kind of a feedstock. And no, unlike manure, we're not going to be able to get any methane offset credit for this because these crops were actually never producing methane. If we left them in the field, they would decompose aerobically just straight to carbon dioxide, which is what will happen when the RNG gets burned. But because these crops are also building soil, and because they are substituting for fossil natural gas, and because they are also producing a lot of digestate, which is carbon that we can return to the soil or store in other ways, we actually can get negative carbon emissions from this. So better than solar or wind if we manage it correctly. And we can also, if we add CO2 capture and storage, as was discussed this morning, get strongly negative CO2 and CI scores. I didn't include that in this particular slide. Now, I mentioned in the upper right, carbon dioxide for sequestration is important to be thinking about for this and other digester gases if we want to get negative CI scores. But I also want to point out again and emphasize that because this material was not going to produce methane as a baseline or base case analysis, we really have to have tight systems. Fugitive leaks of methane from a grass-based digester are going to be a problem because we're not just reducing methane losses, we're actually creating new methane losses, and those should be really, really closely monitored. But I also wanted to emphasize the soil carbon opportunities of that digestate, which not only can substitute for fertilizer, which is the single biggest input to the carbon balance of crops, but also build soil organic matter more rapidly because that digestate carbon has actually been processed microbially, which is the kind of long-lived soil carbon that is the best to add. So that's my introduction, and I think we're going to hold the questions for the end. Thanks.
Thank you, Dr. Tom. Our next presenter is Will Higgins. Will currently works as the manager of grants, and specifically the Horizon 2 Climate Smart Commodities grant that I mentioned earlier. But he also does strategic development work for Raceline Alternative Energy. He's been a key figure in executing the objectives of the Horizon 2 Climate Smart Commodities grant. Our grant was executed formally with the USDA back in September of 2023, and both Will and I have been drinking from a fire hose ever since. So with that, Will.
Thank you, Brian, and thank you to the ABC for having me. My name is Will Higgins. Like Brian said, I am the grant manager for Raceline Alternative Energy. I live in rural central Iowa, and I'm going to talk to you today about our vision, which we call Horizon 2. So just to give a little background on Raceline Alternative Energy, RAE is an owner, operator, and developer of renewable natural gas production facilities. And also we have a focus on incorporating native prairie restoration. And so for those of you who know Raceline or know Rudy, you might have seen this before. This is what we call Rudy's Venn. And so this Venn describes a project model and a revenue model for how we plan to integrate Grass2Gas. And so you can see there the three items of the Venn is energy, ecosystem services, and wildlife habitat. So where those three come together is the vision and the model that we call Horizon 2. This Venn really is also kind of a personal ethos to me. I've worked in the energy industry as well as I consider myself an outdoorsman and a conservationist. And so really this Venn diagram really makes Raceline a really good fit for my personal passions and what I care about. So I want to talk about how we're implementing Horizon 2, and I think really what kind of kicked this off was a sea change. This is a grant that's called Sea Change Grass2Gas, which is a partnership between Iowa State and Penn State that Raceline is an industry partner on, and that was the USDA NIFA grant that focused on exactly what we're talking about, and it was a great to have an introduction from Dr. Tom Richard and explain a lot of the background of why we're here and why we're doing this. So I know it's cool to have somebody else give that portion, and then I can kind of focus on how we're implementing it. But that Sea Change grant really kicked things off into a really momentous and important development, like Brian mentioned, which was the Horizon 2 Climate Smart Commodities grant. And so if you're not aware, the Partnerships for Climate Smart Commodities is a grant program funded by USDA for the integration and incentivization of climate smart practices in agriculture. And so I can't take any credit for For the application, I actually joined Raceline after the announcement was made, but worked with a number of our team that are also here today, literally almost a year to the day, through negotiation to get to a signed agreement with USDA, like Brian mentioned last September. And so the primary use of that $80 million, and the majority of those funds are going to producers, and to incentivize the change in practice, like Dr. Richard mentioned, to incentivize them, provide that financial incentive to grow the cover crop and prairie biomass and integrate that with their operations. And so, that's the primary use of what that funding is going towards. And so I think there was a great discussion as part of the policy session about being specific with our language and what we're talking about. And so when we talk about prairie biomass, currently we're using a 28 species mix, and that is a combination of grasses and forbs. And so that's a diverse mix. And that's what we see as the model. And instead of, a monocrop bioenergy crop, we're using a diverse species of prairie. So that's what we mean when we say prairie or native grass. We're talking about this currently a 28 species mix, and that's something that's been developed by the Raceline team for many years. And then when we talk about cover crop, I personally don't really like the term cover crop. I think it's very broad and can mean a lot of things depending on where you are in the country. And so to be specific about what we're talking about, we're talking primarily about a cereal rye winter crop harvested for biomass. So we call that a winter cover crop, but primarily in a corn-soybean rotation in Iowa and Missouri. So just to be specific about what we're talking about when we say cover crop. We have a number of grant partners. As you can see, there's universities, Iowa State and University of Missouri, as well as nonprofits, as well as other for-profits. And so this, we couldn't do it without all those organizations. There's also many supporters that are not official partners of the grant, such as Pheasants Forever and Seavers Family Farms, that are big supporters and really are critical to us achieving that award, and are helping tremendously with the implementation. So there's 3 goals of the project, and this is a 5-year project that Brian mentioned started last September. And so the first goal is to implement those production practices of the winter biomass crop and restored prairie. And like Dr. Richard mentioned, that will provide better soil health, clean water, flood control, and also can provide reductions in CO2 and other emissions. And so part of goal 1 is to help work with producers to strategically integrate those crops to improve profitability. And so we see the most there's a disproportionate benefit of those environmental benefits and ecological services on marginal crop ground. And so if we can integrate these either prairie or cover crop on that marginal ground, that'll have a disproportionate benefit. And also, those acres are in Iowa and Missouri, there's acres that are historically challenging from a profitability standpoint in a corn soybean rotation. And so really giving those producers another option and another market that Raceline is going to build so that they can and work with them to evaluate and produce another option for them that improves their farm profitability. I thought Patrick Surface had a great moment this morning in his presentation talking about the penetration of biogas project into small and medium-sized farms. And I guess as an owner of a small farm, that's something that's personally important to me. And so this Horizon 2 vision, when we talk about how do we integrate and make biogas projects work at smaller scale for smaller farms, I think the integration of biomass feedstock is critical to doing that, because when we can produce more gas from the biomass, as developers in the room will know, you need a certain number of animals to pay for a biogas project, whether it's the cost of an interconnect or the cost of equipment. If we can produce more gas without raising animal headcount, we can make smaller and smaller farms able to participate in biogas markets. So I really thought that was a great comment this morning, and definitely fits in with our vision for Horizon 2. The other thing that I mentioned was the Venn diagram, and so stacking the revenue sources from renewable natural gas as well as private ecological service markets, whether that be a carbon market or another type of ecological service market that we're working to develop, that will provide the revenue source post. We have 5 years of grant funding to incentivize this, but that's our goal, and really what we have to achieve in that 5 years is to build a revenue model that provides that same level of incentive to continue those practices without public funding. And so goal 2 of the grant is to transparently measure, monitor, and verify. USDA refers to this as MMRV, like we talked about, those practices on a scale. And so the grant is, our goal is 40,000 acres of cover crops and 40,000 acres of restored prairie over the next 4.5 years. And so there is a requirement, I guess, as part of the Partnerships for Climate Smart Commodities program, to do some form of verification. And so, like I mentioned, what we're working to do is work with an ecological service or carbon market partner to do that verification. As well as there's work from the universities, Iowa State and Missouri, to do field trial measurement to better inform models, such as the Comet Farm model that's used by USDA to model the ecological service benefits of those practices. And I think I was going to show a video here, but I think in the interest of time, I'm just going to talk about our goal 3 is that we communicate and provide equitable access to these new markets and value chains to producers that historically have been underserved by USDA. So USDA's definition of historically underserved producer, that includes people of color, women farmers. And so we're working with several partners that, to do targeted and specific outreach to those groups to ensure that we're providing incentive to small and medium-sized farms and also farmers that are historically underserved by USDA. And so the video, and also as part of that, we're communicating that value chain. And so we're doing that in a number of ways, between a video series, podcast series, and also written media. And so if you go to our website, racelinealternativeenergy.com or prairieprofits.com, you can see season 1 of the video series and also the podcast series, as well as we're just kicking off work on season 2. And so that we'll have lots of different types of media to help communicate that to society, to producers, and to the industry as well. And so just to talk a little bit about project status, we did implement about 1,100 acres of restored prairie this winter in North Missouri. Right now we're in I would say a planning and scale up phase. Our goal for this next winter is 7,000 acres of restored prairie implementation. And so we're working and putting plans together to make that happen and achieve that. We're also working on the commissioning and startup of our pilot facility. That's at a partnership at the Horizon 2 facility in Stockton, Iowa, at Seavers Family Farms as well. And so that facility is our pilot facility where we'll be working on the integration of that biomass into an anaerobic digester system. We're also, like I mentioned, we're working and talking to several different folks about securing a partner to help provide that ecosystem service or carbon market payment for producers, and so we can stack that benefit on top of the government USDA incentive, and then, like I mentioned, our goal is to build that so that at the end of the 5 years that we'll be able to sustain that payment level from the different sources of revenue that I talked about. I think also another important thing to talk about as far as revenue generation from the gas is our current, what we're working on is an EPA pathway petition for cover crops and also prairie to be able to generate RINs from integrating those and co-digesting those biomass crops with manure. So I won't talk a whole lot about that other than just from my vantage point, it was very interesting to see. I'm communicating a lot with USDA in regards to our project and project status. And, one of the key assumptions of that project is that we are allowed to generate, and we secure that pathway to generate RINs from the biomass. And so making sure that EPA is talking to USDA and they understand, and so that we have all the different government agencies rowing in the same direction and understand that it's not just one agency that needs to understand this policy. We need that's been an interesting thing to see, and I think USDA was very supportive in discussing with EPA the need for this to happen. And so I talked a little bit about our vision and the project. Rudy has been working on this for a long time, and in a lot more depth than I can go into in this presentation today. I mentioned the different types of media. We do have a book that has just been published called Prairie Power, and so I really encourage you to check that out. And it really describes the history of the vision and a lot more background than what I can provide today. So with that, I'll turn it over to Kevin.
Thank you very much, Will. And our final presenter today is Kevin Munson. And we wanted to tie this all together. You've obviously heard from Dr. Tom and our kind of the academic and research that has gone on for a number of years that he's been working on at Penn State and elsewhere, and others who have been involved in those research projects at many different universities, most of which are land-grant universities. And then, of course, Will's presentation with regard to the Horizon 2 model, where we're taking a lot of the work that's been done in academia and some of the science that's been evaluated here in the United States, plus some of the research that's been conducted across the pond in Europe, and implementing that idea and concept with our Horizon 2 grant. And finally, now that we're coming to that point where, okay, we've got this material, we've got the manure sources, we want to integrate this into a successful anaerobic digester that produces renewable energy of some sort, whether it be RNG or electricity or thermal energy. Why, no better than to have Kevin Munson with WellTech. Kevin is the International Sales Manager with WellTech Biopower. He has 25 years of experience in the anaerobic digestion world in the UK, in Ireland, in Europe, and North America, and South America. He has a PhD in anaerobic digestion biology and process optimization. He's done postdoc research, consultancy, project development, customer relationship, management, and technical sales of turnkey biogas plants for over 10 years with WellTech. So, Kevin, welcome.
Okay. Thanks very much, Brian, for the introduction. I'd like to thank also the American Biogas Council for putting on another great show and for inviting me to talk in this panel. So, yeah, for those of you who don't know me, my name is Kevin Munson, International Sales Manager with WellTech Biopower. We have learned a little bit over the past 15 years about co-digestion, particularly about the co-digestion of grass. So the first thing that I want to say is that once we go outside the US market, co-digestion is normal. Co-digestion is a normal approach. Farms are smaller, factories are smaller, policies and incentive structures by which we get paid for biomethane are different. Manure-only projects don't normally stack up on their own. So most European plants do try to source as many locally available feedstocks as possible to maximize the return on investment from their plant. In Northern Europe, UK and Ireland in particular, grass silage is one of the most commonly co-digested feedstocks. So this isn't either or. We can have all the environmental benefits of carbon negative gas through manure. We can just get more renewable gas when we co-digest, more renewable gas from the same space, from a very similar investment. And in Europe, by the way we get paid, that makes a lot of sense. So a little bit of context, back in the year 2000, Germany brought out a feed-in tariff for renewable electricity production. and there was no stipulation in that whether the electricity was from manures, from wastes, from ag residues, or from crops. So the easiest way to build a plant was to co-digest pig or cattle manure with corn silage. And a lot of plants get built up that way. So other countries followed with the feed-in tariff for renewable electricity: UK, France, Italy, Czech Republic, Greece, to name a few. And what we found when we tried to co-digest grass silage in systems that were designed for maize or manures were some problems. The grass was clumpy, sticky, wet. We had long fibers, high cellulose content, and towards the end of the growing season, maybe some lignin in there as well. There were a lot of examples of, in the early days, of feed system blockages, poor mixing, floating layers and crusts, all of which led to poor biological performance, loss of efficiency, and downtime. So some of the problems from grass: the fibers are larger, hard to digest, high cellulose content, smooth surfaces. We saw blocking of feed hoppers, bridging in feed hoppers, stones and foreign materials coming through and clogging up pumps or accumulating in digesters. The long fibers, if left unattended, would float to the top. And if that crust wasn't broken up, it would form a thicker and thicker crust until we had problems with downtime. And a lot of digesters had to have the roof taken off, the crust taken out, weeks of downtime. So also, high energy requirements for the mixing, high wear and tear in mixers, all the usual problems. So back in 2012, Welltec brought out the multi-mix pre-feed system to solve specifically this problem. The multi-mix enables the feeding and efficient digestion of a high percentage of grass silage, as well as straw-based manure, and other fibrous feedstocks that would otherwise be problematic. We can also pre-process chicken litter, feedlot manure, vegetable waste, or a variety of different feedstocks through this system. So, there's a short video here, and we might skip through part of it in the interest of time, but this shows the technology with a couple of videos. So what we're doing is we're augering the solids into the top of this multi-mix unit. We're reintroducing hot digest state, 40 degrees C, to the front and back. There's an auger running through the bottom of the unit that starts to mulch up the solids and mix them with the liquids. We then go through a stone trap to remove all those stones and foreign materials, and then a maceration unit. After the maceration unit, there's a pump, and we pump the now liquefied feedstock to the digesters. We can serve up to 3 digesters from one multi-mix unit. So this is looking in the top of the unit at the auger. Some solids dropping in, and you see the liquids starting to liquefy them up. So if we could skip on now, that'd be great. Thank you. So a couple of photos of some of the stones. And when you're harvesting grass or vegetable waste or anything off the ground, you can have stones come through, and you obviously want to take those out before hitting your pumps or before accumulating in your digester. We can do that with this stone trap. Also a picture on the left there, on the right, sorry, of the macerator at the end of the multi-mix unit. So some of the advantages, we're processing the fibrous materials such as grass, straw-based manure. We're shredding, homogenizing those fibers and those hard to digest solids. We're feeding them to the digester in a homogeneous, pumpable substrate, like a smoothie. Easy. So, we're removing stones. We can feed up to 3 digesters from the one multi-mix system. This gives the operators, at least in Europe, increased flexibility to accept alternative feedstocks, accept cheaper feedstocks or different feedstocks. So we can also, as I said, reduce the floating layers and sinking layers, reduce the mixing requirements in the digester, reduces the wear and tear in the mixers. We're getting a lot longer lifetime out of the mixing system than we did before we had the pretreatment system. We're reducing the retention time needed due to the smaller particle size, the increased substrate bacteria contact. So better mixing, more efficient digestion all around. So a couple of pictures just of some of the feedstocks that we co-digest in UK and Ireland. We have wet straw-based manure on the left and some grass silage on the right. So what we found from experience is that the multi-mix pre-feed system in combination with our hybrid mixing system shows us very good results. Our bigger digesters will have 6 mixers in each digester, 3 submersibles and 3 biobools like you see on the right there. I'll not go into why that mixing system gives us such good results, but if you are interested, come and see us on the stand, 516, and we'll bore you to death with it. It's a lot of science in there, and it works very well. So the benefits to efficient mixing: no dead zones, no channeling or rat runs through the digester like you can get in plug flow systems or less well-mixed systems, less energy needed to mix, less wear and tear in pumps and mixers, quicker retention time, all around more efficient digestion, less residual biogas. So this next short video shows inside, looking in the window, the porthole of one of our co-digestion systems, processing grass and straw. And you see there a great mix. That's what you want to see. Now, the mixing system might only be working for 10 minutes every half hour, 10 minutes every hour, but when it is mixing, what a great mix. So a couple of quick case studies. We have 417 plants built around the world over the last 20 odd years. We did a little calculation. We totted them up recently as part of a due diligence process. We calculate that about 95% of our systems around the world are co-digesting something or other. So only about 5% of them are manure only. So co-digestion is normal. So this is a pig farm, Northern Ireland, not far from Belfast. Co-digesting pig manure, 6% dry matter, and grass silage. So you see the pig sheds on the right, scraper system, scraping the pig manure into one of 4 pre-tanks along that central channel. And our control system takes the liquid manure from there, doses it to each digester in the right ration every hour. Every morning, the plant owner operator will load their feed hopper with grass silage at the right tonnage, and our control system from there feeds the right tonnage from the hopper to the multi-mix and pumps the right volume to each digester. Very successful system, simple. These guys also have a screw press separator for their digestate. You see it up in the gantry there on the left and the end product on the right. So one of the added benefits of adding ag residue or crop to manure digestion is that the digestate has more structure. The screw press separator has more to press against, and you can have a higher quality solid fraction of your digestate that can be used for bedding. So these guys also have a beef unit, and they use this solid fraction as bedding for the beef unit and sell the excess to the neighbours. The liquid fraction gets stored and land applied in spring and summer. Most of the NPK is still in there. So another case study, commissioned 2016, cattle manure, chicken litter, grass silage, and a little bit of whey wastewater. Similar principle, solids into the feed hopper, through the multi-mix, liquefied, and pumped to the digester in the right ration, liquids through a pre-tank, through our central pumping unit in the right ration to the digesters. Very successful plant, this one, over 98% uptime every year since we commissioned it. So good plant, good operators here. And the last case study, quickly, a vegetable grower and packager, co-digesting vegetable waste, so carrots, potatoes, turnips, cauliflowers, all kinds of waste vegetables, co-digesting with chicken manure, cattle manure, grass silage and a little bit of corn silage as well. Another very successful system. So some quick conclusions. Grass2Gas, it's technically possible. We've been doing it for more than 10 years. We can consider it proven. There are a lot of benefits when it's done right. The other guys in the panel have alluded to some of this. They know this in this part of the world better than me, but cover crops, winter crops, income from marginal land, farm diversification, more income to rural areas, soil improvement, production of sustainable bedding, more renewable gas from the same plant or similar investment, ultimately more fossil fuel displacement using locally produced or locally available renewable resources. So look, again, like I said at the start, we don't want to lose the carbon negative benefits of that manure. That's great, but this isn't either or. We can have all those benefits, all those environmental benefits from digesting manure, and we can get more renewable gas from the same plant. So carbon negative is great, but renewable gas is still good. And we can have both from the same plant. So I think it can make sense in North America too, if there is a pathway to payment. So thank you very much. Most of you still awake. Thanks for that. If you have any questions, we can see what we can do on the panel. And yeah, if you want to speak privately about anything you've heard, come and see us in booth 516. We have some of our biology department here and some of our engineers as well. So you'll get some good answers. Thanks.
Let's give these gentlemen a hand. So normally this is the time when the moderator might, prompt a few questions to our panelists, but in the light of the time, I think we ought to just go right to the group. Are there any questions from the audience for our panelists? Yes, sir.
Is then the final product digestate used for humus for farm? Is it the same as the compost product? Anaerobic.
So let me summarize. We do have a mic here too, but I think I can summarize your question. Is the digestate or the product that we're producing in our anaerobic digestion facilities, especially in a co-digestion process like we've just talked about, is that as valuable of a product, soil amendment, as what we might get otherwise from other types of digesters, maybe just a manure-only based digester? So I will turn it over to one of our panelists.
And I'll start. So first of all, I should disclaim that I spent the first 20 or so years of my career working mostly on composting. And I know that world really well. And some of my friends there would be a little upset with what I'm about to say. Because digestate, as far as I can understand it, and that we do need to understand more, is actually better than compost in a couple of very important ways. The first one is that there's been a lot of microbial processing that's gone on in either one of those systems. And the long-lived organic matter in soil, the soil microbiologists and soil organic chemists have understood over the last decade or so, is really microbial waste. It's not, we used to think it was like the lignin and the non-degradable parts of the plant, less degradable parts of the plant, which actually degrade less in anaerobic digestion. But no, it's the bacterial processing and their waste products that really are the long-lived stuff. So maybe roughly equal there, but in the digestion process, we do multiple cycles of those, and it typically is a really deep process. But the other thing that's important in that comparison is if you take the kinds of feedstocks, and we do have to have nitrogen in our feedstocks, either composting or digestion, the nitrogen in a composting system is largely lost. So if you're doing food waste composting or wet grass composting or manure composting, you could lose 50, 60, 70% of the nitrogen as ammonia to the atmosphere, which actually was probably happening in a lagoon that wasn't a digester with manure on many farms too. When we digest, we capture that nitrogen. We've got a contained, closed system, and we keep it in solution so it's actually available to the crop And that's another very important advantage of digestate over compost. So compost is good, digestate is better. Many other benefits. Energy absolutely is one of them.
As our company founder and partner, Rudy Raceland would say, you maximize the ecosystem services from this process. And it's not just focusing on one or two benefits, it's focusing on a number of potential benefits, whether it's maximization of the nitrogen in that digestate from the ammonia that is captured in the digester and becomes a part of that digestate, or it's the reduction of greenhouse gases, or it's the organic matter going back into the soil when you apply it to the soil, or whether it's the habitat that's created when you use prairie as a feedstock, because we're not harvesting prairie every year necessarily. We're going to leave some there for the wildlife and conservation benefits that are provided. You know, the list goes on and on and on. And that's the thing, I've said this for probably 15 years, going back to about 2009 when I started to do our research in our digester facility. I said, the way I looked at it, there is no other form of renewable energy production that maximizes or provides as many benefits to society as what anaerobic digestion does. None, not even close. When you look at solar, wind, even throw nuclear in there, there's just nothing that even comes close to maximizing the benefits that can be derived by society than what we do through anaerobic digestion. And especially now when you integrate other potential feedstocks, you know, we're expanding the universe or the size of that pie. Anybody else? More questions? Yes.
It was great to hear about the rotation of crops and the crop cover, but I don't understand how you can feed the digester all year round if the crops are seasonal. Can you elaborate how you would balance supply 12 months of the year?
Yeah, sure. So what dairy farmers do in Europe and anaerobic digestion owner operators is we harvest our grass through the spring and summer, usually 3 or 4 cuts, and we make silage from it. So we slightly acidify it to make silage, and we keep that in clamps, and then the farmers feed the right ration to the dairy farms and to the digester every day.
I might also just give an example of how the harvest of that biomass that can be utilized in anaerobic digestion also helps in other ways. We were out at near Lancaster, Pennsylvania last summer on the Brubaker Brothers dairy farm. They have about a 1,200 cow dairy. They have a digester on site. They grow cover crops on everything on their farm. I think it's around 1,200 acres of cover crops. They harvest about half of that cover crop acreage as feedstock for their cows now. They've eliminated the use of alfalfa. I mean, alfalfa and dairy are as synonymous as you can possibly imagine for generations. They don't use alfalfa in their feeding rations anymore. It's now cover crops. Why do they use it? Well, number one, they're maximizing ecosystem services. They're cleaning up their water by extracting any excess nitrate, nitrogen that might be in the soil. They're in a wellhead watershed protection area, so they have to be very careful about what they're putting on their soil. So they've eliminated a lot of the synthetic fertilizers. They're extracting excess nitrate, nitrogen from the cover crop. However, the other half of the cover crops that they're seeding, I asked them, what are you doing with that? Well, we're just terminating that and using a non-selective herbicide to kill it. So have you ever thought about adding that to the digester? And they said, no, that's a good idea. And they were actually looking at potentially expanding their digester facility anyway. So it's just one of those things. Even really bright, I mean, Brubaker Brothers Dairy Farm has been around for probably close to 200 years in that part of Pennsylvania. They're very smart farmers, very smart dairy producers, but it just never dawned on them that that could potentially be another feedstock for their digester and actually add more revenue, increase the potential benefits as a result of cover crop production, as well as, diversify the risk or maximize their risk-bearing ability through additional diversification. Any other questions? Seeing none, it's 3 o'clock, so perfect timing. Thank you, everyone. Let's give these gentlemen another round of applause.